In the last few videos, we've been discussing heat and work and heat engines, and now it's time to discuss a new way that we'll be able to compute the work done in a cycle, utilizing the fact that the cycle is closed. To be able to do that, I'm going to need to introduce a new concept within differential geometry to you, which is the concept of a two-form. So let's start off the video just talking about two forms. To do that, first, I'm going to have to introduce a new object to you. Suppose that we have a one form, let's say omega, and another one form, let's say mu. So let's say omega and mu are one forms. Then one type of two form, which I'll define more carefully in a second, is an object omega wedge mu, where this is called the wedge product. So all I'm saying here is that if we take the so-called wedge product of two one forms, we'll get a two form. Now the wedge product satisfies a few properties. The first is that it's linear, so omega wedge mu1 plus mu2 would be equal to omega wedge mu1 plus omega wedge mu2. It's also linear over scalars. So if a is a real number, or even a complex number, although we won't be working with that here, then this is equal to a times omega wedge mu. And finally, maybe most importantly, it's antisymmetric. So omega wedge mu is equal to minus mu wedge omega. All right, good. So if this is one category of two forms, then how do we get all of them? The answer has something to do with the exterior derivative, which we introduced before. So before, we discussed that the exterior derivative is a function from functions on gamma to one forms on gamma. And we discussed that we could write a basis for the tangent space, sorry, for the cotangent space at x by dAI if AI is a basis. Now, I'm going to claim that the space of two, or I'm going to just label the space of two forms capital omega 2 on gamma. And I'm going to state without proof that this is just equal to dAI wedge dAj, and sorry, the span of this. But let's note that the antisymmetry actually has an important consequence. So again, this is antisymmetry. So the corollary is that omega wedge omega must equal minus omega wedge omega. But the only time an object can equal its own negative is when it's 0. So this object is 0. So here, in principle, we only need to consider I not equal to j. And in fact, because we could always permute the two basis vectors, basis one forms, we could only consider I less than j. Okay. And actually, let me be a little bit more clear. Let's denote by omega 2 at x, gamma, the space of all two forms on gamma evaluated at x, which is then equal to the span of these two vectors evaluated at x as well. That's a little bit cleaner of a statement, and so should fix any sort of um, basis issues. Okay, wonderful. So now, let's extend the exterior derivative as well. Whereas before, we had D going from functions to one forms. Now, we'll also allow D to go from one forms to two forms. Oops. And how does it do that? Well, if we act by D on omega, we know that omega has an expansion in the basis. So that will be omega sub I, dAI. And now we can be a little bit more specific. This is going to equal the partial of the partial with respect to AJ of omega I times dAJ wedge dAI. Now, I want to actually sort of unpack this a little bit. Like, why does this formula make any sense? And the answer is that we basically just want D to obey the Leibniz rule. Remember that that's what it did before. We had D of FG is equal to dF times G plus F times dG. Now we want to think about that happening again. So d omega I dAI will equal d omega I. And then we need some way of multiplying. Let me just put a big circle there for a second. Times dAI plus omega I times d dAI. Good. Okay, so we need two sort of rules in order to fix this. First, we need to know what's going to go in here. And second, we need to know what this object is. The answer to what goes in here is that it's the only multiplication operator that we have that acts on two one forms. Remember that because omega I is just the coefficient, it's a function. And so d omega I is a one form. And the only way we have to multiply these two one forms is to stick the wedge product between them. All right. On the other hand, we need something that tells us what happens when we act by D on dAI. And here we're going to introduce a very important rule. The rule is that D squared, in other words, D composed with itself, is always equal to 0. And that's so important, let me actually mark it here in red. Wonderful. So now let's check that this actually gives us what we had above. So d omega I, we know we can expand that out in a basis. We've done that calculation before, and in fact, have done it in the last couple of lectures. This is just dAj omega I times dAj. And I should have said partial sub aj of omega I times dAj. And then wedge dAI. But notice that the equation I'm underlining in blue is precisely the same as the definition that I gave up here, which I'll also underline in blue. Okay, good. So now we have a sense of what the exterior derivative does to two forms. Now we're ready to introduce Stokes' theorem again. And this is really getting at the heart of what I wanted to cover today. There we go. Remember in the last video, we had that remember that in the last lecture, we had that Stokes's theorem said that if I evaluated df along a curve C, that was equal to f of C of B, if the curve ran from A to B, minus f of C of A. But those of you who have taken a vector calculus class may notice that Stokes's theorem is actually much more general than this. And today we'll introduce that more general notion. So suppose that we have a surface, a two-dimensional surface, which I'll label S, not to be confused with the entropy. So maybe actually I'll use curly S. Good. And suppose that on curly S, I have a 2 form that is the exterior derivative of a 1 form. We'll also use the term exact again to describe 2 forms like this. So we have an exact 2 form. Then this is the same as the line integral of the 1 form on the boundary of S. Okay, so we use this partial symbol for the boundary. And you may have seen that in a math course before. So let's draw out what's going on. Suppose that we have our our region. So S is this region in here. And then the boundary, which is oriented, is the counterclockwise loop here, partial S. And so if we have the 1 form, d omega, and we take a surface integral of that 1 form on this interior region, then that is equal to the line integral of the 1 form omega on the boundary. Now you may notice that I didn't explain one thing to you, which is how do we evaluate the left-hand side? How do we take the integral of a 2 form over a two-dimensional region? And the answer is we do a surface integral. Now, rather than go through all of the complicated differential geometry to show you exactly how to do this in the most general case, I'm going to rely on something that we talked about in an earlier video. If we work in a coordinate system for a line integral, suppose that we work in a coordinate system such that only one of the coordinates varies. We call that coordinate A, and then we have a function g of A, B, C, and possibly other coordinates times dA along the curve C. Again, so that B, C, etc. are fixed on C. Then we learned that this integral can be treated like an ordinary one-dimensional integral over A. We're going to use the exact same methodology to evaluate 2 forms. So now, suppose that we have some function, we'll still call it g, of A, B, C, and so on, dA wedge dB, so that C and so on are fixed on our surface S. This integral is just an ordinary area integral. Good. Okay, so now we have Stokes's theorem. We have the notion of two forms. Let's figure out how we might be able to apply these things. Okay, so back to heat engines. Let's draw the example that we've been working with. So here's our P and V space, and we'll have a cycle that goes clockwise. So we have one isothermal side, one isobaric side, and then one isochoric side. Good. And we would like to figure out, say, the heat or the work. Let's call this curve C. Well, we've already done this with line integrals in a former video, but let's see if we can do it using surface integrals. The key trick to notice is that C is the boundary of a region, which we could call S. So again, S would be this interior region. And C is actually the opposite of the boundary. So maybe I should say minus C is the boundary. And I say that because C goes clockwise, whereas we know that a boundary should go counterclockwise. Good. So now I can use Stokes's theorem. Remember that the line integral that I'm trying to compute, say for let's actually start with work, is equal to minus P dV evaluated on C. But this is then equal to minus the integral over minus the partial of S, I should say, of P dV. And the rule here is that if you're going in the wrong direction, this just causes it to be the negative of the integral. So we can just flip the sign outside and now say that this is plus the integral over the boundary of S of P dV. Good. Now, just going back to Stokes's theorem, I'm supposed to compare the line integral over the one form with the surface integral of the exterior derivative of the one form. So this is then going to be the integral by Stokes's theorem over S of the exterior derivative of P dV. Now we'll need to evaluate this using the Leibniz rule, I should say. Good. Okay, so we get dP wedge dV, we saw that before, plus P wedge, or maybe just times d dV. But we know that d squared is equal to 0. So this term is 0. So this is just equal to the integral over S of dP wedge dV. But that's good news because we know that if we have a function here, let's just insert the function 1 here, so constant function 1. We know that if we have a function times dP wedge dV and a surface that's bounded in those two coordinates and with all other coordinates fixed, so in this case n is the other coordinate and it's fixed, then we're golden. We can just evaluate this as the integral on the inside of this region. But what is the geometric meaning of the integral in PV space of the interior of this region? It's just the area of S. So this is just equal to the area of region S. Good. Now let's find that area. We'll say that this is a volume, or sorry, is a pressure P naught, and this is a pressure P. I think that's the labels that we've been using. Similarly, let's suppose that this is a volume V, and this is an isotherm. So we have, let me do this in a different color, P naught V is equal to N kBT, but that's also equal to, we call this V naught, PV naught. So we should choose some of these to be sort of independent variables and others to be dependent. Let's, for instance, just to make our lives a little bit easier, choose P naught to be independent and P to be independent. And then we can also choose, let's also choose V naught to be independent. And then that will determine V. Okay. So now let's figure out what the area of this region is. Well, actually, it's not too hard to compute because we can now just use regular geometric tools to do it. It'll be the integral of the whole area under this curve, which includes this region down here, minus this region that I've now highlighted in green and crosshatched. Okay, so let's do it. We know that this curve up here is the curve V is equal to N kBT over P. And furthermore, N kBT is equal to P times V naught. So let me maybe say that this is V of P prime. And this is equal to P times V naught over P prime. Good. Yes, that gives us exactly what we want. Okay, so this is equal to the integral from P is equal to P naught to P is equal to P of P times V naught over P prime dP prime. But this overcounts, right? Because we don't want this rectangle. But this rectangle has an area that is relatively easy to figure out. Its length horizontally is P minus P naught, and its vertical height is V naught. So we just say minus V naught times P minus P naught. Good. Now let's take this first integral. Notice that P and V naught are constants, so they come out. And then the integral is just log of P prime, evaluated on the two sides at P and P naught. And then we can use log rules to finish this off. So we get P V naught times the log of P over P naught minus V naught P minus P naught. And you can check from results that we've already shown that this is correct. Now there's a lot more that we could do with this. And in particular, it would be very interesting to take this figure and put it into TS space to figure out what we get there. But so that this video doesn't run too long, I'm going to allow you to do that yourself. So until I see you again, thank you so much for watching.